Let's get started. The second half of Unit 2. Last time we finished talking about forces and momentum. That's last thing we talked about. So now let's move on to the next little bit, which is the turning effect of a force. Friendly reminder, this little nice checklist is there for you to read and, check to make sure that you understand the different points in there. So if you read something and you understand it, give it a check. If you don't, you need to revise that point again. So let's talk about the turning effect of a force, what we call a moment. So the question is, what is a moment? Moment is defined as the turning effect of a force, meaning when you apply a force on an object can rotate. Now, this is different from circular motion. It's not the same thing as circular motion. So when you apply a force on something, it turns. Now, objects can either rotate clockwise or anti-clockwise. So clockwise is this way, anti-clockwise is this way. But then how can I tell if something is going to rotate or not? There is one very important bit. The object must have a pivot. Like there has to be a fixed point on the object that it pivots around. Now, if you have trouble figuring out if something is going to rotate clockwise or anti-clockwise, my piece of advice is always what? If you have a diagram like this, and here's your pivot, and I give you a bunch of forces, let's call this F1, and let's call this F2. What I want you to do is take your pencil or pen, put it on top of the sheet of paper, hold it with one of your fingers, like one of your hands, where the pivot is, and then give it a shot, like try to apply a force to see how F1 and F2 will make this thing rotate. So F1 is on the right side, pushing up, so it goes anti-clockwise. All right. F2 is on the left side, pushes up, so it goes clockwise. Okay. How do we calculate moment? It's force times perpendicular distance to the pivot or from the pivot. What do I mean? I mean that the distance between the force and the pivot has to be at 90 degrees to the force. Like it has to be at 90 degrees to the force. Most questions, that will be the case. It will not be an issue when we solve. However, sometimes, and when I say sometimes, I mean it has only happened once. Okay? Sometimes the question will not give you the distance already perpendicular to the force. Sometimes, like in this special case, the force is already at an angle to the surface. So what distance do I use? Because this length over here is not the correct distance. Like if this was, let's say, 50 centimeters or so, this distance is not 50 centimeters. It's not perpendicular to the force. So what do? You need to find the distance that is perpendicular to the force. So you draw a line from the pivot to the force. And that line needs to be at 90 degrees. This is a very rare scenario. It's only ever happened once in exams. But who knows? You know your luck. Yeah. But wait, how do I get this? You said draw the line. Okay, I've drawn the line. How do I get this length? Whatever you draw, this will always end up being a triangle for you. Whatever you draw, this will always be a triangle for you. So using trigonometry, and think about it a bit. If this is 30 degrees, this is 30 degrees, and this is called L. What's this? Which is the opposite of the angle. Sine 30 equals opposite over hypotenuse. D over L, which means D, which is the distance I'm looking for, is L sine 30. So keep that in mind. This only will be used if and only if the force is not perpendicular to the distance given. Again, this has only happened once. Now, if you move where the force is, if I change the position of the force, so let's say you apply a 10 Newton force here at a distance of 100 centimeters or so. Instead, if you start moving closer, what's going to happen? In order to apply the same moment, you need to apply more force. If you move even closer, you need to apply even more force. So keep that in mind when thinking about where should you push your object. If you want to apply the same moment, the closer you are to the pivot, the more force you need. So if I ask you, hey, where should I push the object with the least effort? As far away as possible from the pivot. The best position is the furthest point away possible from the pivot. Okay? Yeah. So moment is force times distance. That's easy. I just write F times D, but you know it's perpendicular. If I ask you to define moment, define it with the formula in words. Force times perpendicular distance to the pivot or from the pivot. That's right. Yeah. There is a state called equilibrium. When I say that an object is in equilibrium, it means it's perfectly balanced. But you need to say two conditions for equilibrium. What are they? That there's no resultant force, meaning the upward force equals the downward force, or left equals right, and there is no resultant moment, which means clockwise is equal to the anti-clockwise moment. We're going to see this when we practice. Like, this is the most important bit, like the whole clockwise equals anti-clockwise moment. It's almost always used in every single question. Like, yeah, this is the question where we'll use both clockwise equals anti-clockwise moment and the angle trick. So keep it in mind when we start solving. Next up, when it comes to moments, we have to keep weight into consideration because the force of gravity or weight is a force that could cause a moment, especially if the pivot is not in the center of the object. But where does weight act? We always assume that weight acts at the center of gravity or center of mass. Same thing for us for now, which is a point in an object where weight is considered to act. Because realistically, gravity acts at every single point on an object, not just the center. But we simplify things and say gravity acts at the center. Okay? Next. If you have a regular object, the center of gravity is always in the middle, perfectly in the center. Cool. The term often used in exams is the word uniform. So if you have a uniform beam, a uniform object, a regular shape, it's in the center. If it's irregular in shape, like this thing over here, it'll be closer to what? It's not going to be in the center. It'll be closer to the heavier side of the object, like the thicker, heavier side of the object. Heck, if you have a hammer, so think of Thor's hammer, Mjolnir. Like if you have the hammer, which is made of wood and metal, I'm not going to get into the lore though. The center of mass can never be in the middle here because the metal is more dense and has a lot more mass. So it's going to be shifted towards where the metal is. Usually it'll be somewhere here. The center of mass of a hammer is usually in the hammer head. So you got that. Good. That's center of mass. Easy peasy. How do I find the center of mass of an object? If it's a regular shape, it's in the center. If it's irregular, it's near the heavier side. But sometimes you'll be asked to find the center of mass of what we call a plane lamina, like a piece of paper. This is called a plane lamina. The word plane doesn't mean an airplane. No. A plane is, let's just say, a flat surface that exists in two dimensions. It's like the XY or the YZ. This is called a plane. A lamina means a very thin sheet of paper. So it's a flat sheet of paper or flat sheet of card. I don't care what the shape is. Could be irregular. But the word plane lamina means a flat piece of cardboard or sheet or something. How do we find the center of mass? Easy. You hang it from any point, from any corner. Corners are the best. And then we attach what we call a plumb line. It's literally just a heavy ball, like pendulum bob, and a thread. That's all. Wait a second. Why do we need the plumb line? Because if the object is hung from a corner and you let it rest, the center of mass has to be somewhere below where the pivot is. Because if it's not at rest, if I tilt this piece of paper to the right, it'll fall back down and come to rest. If I tilt it to the left instead, it'll fall back down and come back to rest in the center. So the center of mass is going to be somewhere here. So I need the plumb line to help me draw the line. So I usually attach the plumb line, make a mark on the paper. So I make a mark on the paper so I can draw this line. And then I hang that same sheet of paper again, but from a different corner. So you can hang it from B or you can hang it from C. And then you do the same thing. You hang it, you let it rest, put the plumb line on, and draw the line. If the points intersect, sorry, if the lines intersect, that point is the center of mass or the center of gravity. Okay. But this is a technique that only works with sheets of paper. If it's a bigger object, thicker, three-dimensional, ignore that. You'll study that in engineering. Next up, stability. What is stability? It's the ability of an object to avoid falling over. You don't need to define it per se, but basically, if you tilt an object, like if I have a bottle of water over here, and this is a piece of card on the bench, if you tilt this, not a League of Legends tilt though, those players can get tilted by anything, not a bottle of water. If you tilt this, is it going to fall over or not? Ignore the slipping part. Let's say you put a small block here to stop it from falling over. But can it topple over? It's not going to slide. Can it topple over? Yes, it can. But when does it topple over? Center of mass is the key. If the center of mass is here, obviously the object's not going to fall over. But when the center of mass, which is where the weight is acting, crosses over the edge of the object, this creates a clockwise moment, so it falls over. So when does an object fall over? When its center of mass crosses the edge. So if you tilt this bottle just a little bit, it doesn't. It just goes back. But if you tilt it enough, it'll go over the edge. But if you tilt it so that the center of mass, like let's assume that you're a magician and you manage to tilt this bottle so that the center of mass of the bottle perfectly aligns with the edge of the object, which acts like a pivot. If the center of mass acts perfectly through the edge of the object, what's going to happen? Nothing. It won't fall over. It'll be perfectly balanced. All right? So this will not fall over. Now, how can we improve the stability of an object? You can do two things to improve stability. When you lower the center of mass or make the width of the base wider, which means, and let's erase this bottle. I don't need the stable bottle here. Which means if you have two objects in front of you, and this is a pet peeve of mine, if you have two objects in front of you, one is a nice, thin, delicate glass. You know those glasses that they always serve like very fancy drinks in or wine in or something like that? Or like the glasses that your mom only pulls out when there are guests around. And my good old mug. Both of these have the same width, right? On the floor, on the bench, on the table, they have the same width. If you fill them both up with an equal amount of water, so it's the same water, the center of mass of that fancy cup is much higher. Center mass of the fancy cup is higher. The center mass of the mug is lower. So if both of these are on a tray and the tray tilts a bit, or somebody just hits the top of this bottle, and I hit the top of the mug, oh yeah, this glass, I said bottle, this glass is going to definitely fall over and break. I hate these things. They break all the time. My mug, however, you know, sturdy like a nuclear bunker. It'll survive more than I would. This is if the center of mass is lower. So lower center of mass, more stable. Means more stable. Higher center of mass, you're less stable. Next, what if the objects in question have the same height or have the same center of mass? What if you have a car? You're looking at the car from the front, so you have a car. Right? And you have a motorcycle or a bicycle. Both of them have roughly the same height of the center of mass. So the center of mass for both are roughly the same here and here. So they're equal in terms of their height. But which one is more stable? As in, if the ground tilts a bit or you give it a little shove, oh yeah, the bike's definitely falling over. Whereas the car will not fall over unless the entire floor just flips it over and tilts. Because the wider the base, the more stable it is. And the narrower the base, the less stable it is. Okie dokie? So that's stability and the things that affect stability. Let's solve a super duper hard question. That one singular question that has ever showed up with the distance at an angle that you need to solve. Let's zoom in here. If any of you have never been rock climbing before, it's really good. I've been rock climbing before. I've climbed mountains in Dahab before. It's such a good experience. So much fun. Too bad my rock climbing gym just closed off like a year ago. Haven't been able to climb since. A rock climber of total mass 62 kilograms holds herself in horizontal equilibrium against a vertical cliff. She pulls on a rope that's fixed at the top of the cliff and presses her feet against the cliff. Now, I don't see where the pivot is, right? I don't see where the pivot is. He hasn't said so yet. I'll show you the keyword to look for when you want to find out where the pivot is. But first, he says, calculate the total weight of the climber. Oh, that's easy. W equals mg. So what's the mass? 62. And again, this is an old question. Back then, the value of g was 10 before 2023. However, nowadays, we use a g of 9.8. I'm going to use 9.8 just to get you used to the same thing. So 9.8 times 62, this gives me 607.6. Okay, newtons. Cool. State the two conditions needed for equilibrium. Resultant force is 0. You can also say no resultant force. Resultant moment is also 0. You can also say no resultant moment. That's also fine. Next. The climber's center of mass is 0.9 meters from the cliff, which means this is where her center of mass is. Do you know what that means? This is where her weight is acting. So that's 607 or 608 newtons acting on her comes from this point over here, 0.9 meters from the cliff. Calculate the moment about her feet. The word about something means that is her a pivot. That is the pivot. About her feet due to the weight. So moment is equal to force times distance. So it's 608 or 607.6 times 0.9. That's 547.2. 547 is good. Newton meters, because it's force times distance, so Nm. Nice. So that was easy. Simple, basic. Where's the difficulty? Hold on. Let's have fun. The line of the rope meets the horizontal line through her center of mass at a distance of 1.2 from the cliff. The rope is at an angle of 60 degrees to the horizontal. Determine the tension in the rope. This is just a fancy way of saying, what is the force in the rope? Not the 3 mark question. Exactly, the 3 mark question. All right, look at it, smiling menacingly at you. Is she in equilibrium? Like, is this woman in equilibrium? She is, right? She's stationary, she's not moving, so she's in equilibrium. Plus, she holds herself in horizontal equilibrium, which means the clockwise moment equals the anti-clockwise moment. I don't care what the question shows, by the way. If this is the pivot, then this is a beam. I don't care that this is a human being right now. To solve this question, I just want a simple diagram. This is literally 608 newtons at zero point 0.9. So this is clockwise because it's rotating this way, clockwise. And then the tension, which I'll just call F, is an anti-clockwise moment. It's trying to lift her to the other direction, like pushes her to the other side. But is the distance between the pivot and F 1.2? No, they're not perpendicular. So what do I need to do? I need to draw a line from the pivot to the force. So what is this distance over here? If all of this is 1.2 and this angle is 60 degrees, then the distance is equal to L sine 60. Not 30 this time. In my previous example, it was 30. Now it's 60. So it's 1.2 sine 60. So going back to the question and how do I find the tension in the rope? She's in equilibrium, which means the clockwise moment is equal to the anti-clockwise moment. Clockwise is her weights moment, which we already have, by the way, the 547. We already have that. It's already calculated for us, or like we actually got it. So equals the anti-clockwise moment is the tension in the rope. So force times distance. What distance? So 547 equals F times 1.2 sine 60, which means F is 547 over 1.2 sine 60. 547 over 1.2 sine 60. This gives me 526.35. Well, 526 is fine. Newton. This is force, tension, so it's Newton. Okay? Again. Where did I get 1.2 sine 60? Remember, we did that here already. I told you I want this distance d, the d at an angle. So when I draw this line, this is a triangle now, which means sine 60, which is the angle, equals d over 1.2, because that's your hypotenuse, which means d is equal to 1.2 sine 60. Okay? All right. Good. Next up, after moments, we have power or energy, work and power. Very important chapter. What is energy? Something that you need to live and exist, right? Like all of you know what energy intuitively means. But I just want you to realize a few things before we start talking about energy types and such. First, energy is a scalar quantity, meaning it does not have a direction. Second, the unit of measurement of energy is called joules, right? That's if I'm using SI unit. And third, energy is a property that everything has, but depending on the action or the current state of the object, an object can have different types of energy. So let's go through the different types so we understand it better. First, most importantly, is kinetic energy, which is the energy of motion. So if you're moving, you have kinetic energy. The faster you're moving, the more kinetic energy you have. You can calculate this using half mv squared. You only have two energies with equations, by the way. Technically, like three, because we study heat energy in thermophysics, and there's an equation for it with the specific heat capacity. But for now, half mv squared. Gravitational potential energy, or just gravitational energy. This is the energy stored in an object because of its height. So the higher the object goes, like if you lift an object up, like if I lift my calculator up, you have more gravitational potential energy. And that is calculated using mgh. M is obviously the mass, G is 9.8, and H is the height, or the change in height. It depends on how much it has moved. Oh yeah, V is speed or velocity, so I'm sure you know that. Chemical energy. This is the energy in food and fuel and batteries and so on, and human beings and plants and animals. So the energy stored in us when you eat, that's chemical energy. Elastic or strain. This is the energy stored in an object when it is stretched or compressed or bent. So when I used to play archery and I used to pull on my bowstring, like, the energy stored inside the bow because it bends is elastic energy, right? It doesn't have to be stretching, could be bending, could be compression, okay? Nuclear energy. This is inside the nucleus of an atom. Any nucleus has energy inside. This energy is released during nuclear fission or nuclear fusion. Okay? Then finally, thermal energy, or not really finally, but you see, thermal energy, also called internal. So if you see the word thermal, internal, it's the same thing, it's just heat. Internal energy is the total kinetic energy of the molecules in a substance. And this is affected by temperature. The hotter an object is, the more internal energy a substance has. The molecules move faster. And the cooler an object is, the slower the molecules move inside. And then you have electrostatic or magnetic energy. We don't really see these a lot. We just call it electrical energy for short. But this is the energy stored inside an electric field or a magnetic field, or just the energy stored or transferred by a charge. So electric energy is the energy transferred by a charge. Before I talk about how we can convert energy types, you have a question. How can energy be scalar when velocity is a vector? Because velocity here is squared. The direction won't matter. Remember how we said changing the direction changes the sign convention? Like maybe if you're going to the right, it's positive, and left, it's negative. So technically that should change the value, right? No, it won't. Because if I'm calculating the kinetic energy of an object with a mass of 1 and a speed of 1, because I want to simplify things, positive 1 or negative 1. What's 1 squared? 1. What's negative 1 squared? 1. The negative sign goes away. So when you square something with a negative sign, negative times negative is positive. So the change in direction does not matter at all. So energy cares nothing about your direction. If you're using up fuel, my car doesn't care about if I'm driving up the road or down the road. I'm using fuel anyway. If I'm going north or if I'm going south, I'm just using your fuel. Matters is how much fuel I'm burning. Okay. How do we transfer energy? Forces are the primary method of transferring mechanical energy. We call it work, doing mechanical work. So when you apply a force on an object, it moves, it gains kinetic energy, or maybe gravitational, or maybe elastic when you stretch it. Electrical currents, or just currents, transfer electrical energy. That makes sense. Heating transfers thermal energy. Cool. Waves transfer light or sound energy. So all of these are just different methods of transferring energy. But the most important thing ever, right? The most important thing ever, and I'm going to delete this or like move it aside because I'm going to need this space, is the law of conservation of energy. Energy cannot be created or destroyed. It can only be changed from one form to another. So if I'm running, I lose chemical energy and I gain kinetic energy if I'm moving faster. If I'm climbing, I lose chemical energy and I gain gravitational potential energy. I'm talking into a microphone. I'm converting my sound energy, which came from my chemical energy first, so chemical to sound, and then the microphone changes the sound to an electrical signal. You guys can hear me. So the speakers that you're using to hear me or the earphones change electrical energy to sound energy. But energy cannot be destroyed. It has to be converted. You can't just create a fireball out of nothing. If magic was real, that would be cool and we'd have new physics. Imagine Newton's law of, magical energy conservation. Like that would be kind of funny. But still, people would have probably destroyed the heck out of magic if it existed with science, right? They would have turned magic into a science. But still, how do I use this? Most of the time, just describing it is fine. But sometimes questions need you to use these formulas, the kinetic energy and potential energy formula. The most common trope here, is if you drop an object from a large height, and it starts to fall, eventually it reaches a certain speed right before it hits the ground. So what are the energy changes here? Gravitational potential energy changes into kinetic energy, and they're both equal. The potential energy at the top is equal to the kinetic energy at the bottom, which means mgh is equal to half mv squared. The m's can cancel out. So what does that mean? This means that if I give you the height, h, let's say it's 10 meters or so, you can get the velocity. You can find the speed at the bottom of the drop. So 9.8 times 10 equals half times v squared, and you solve for v. So 9.8 times 10 times 2 square root the answer. Square root the answer. You end up with a speed of 14 meters per second at the bottom. So it starts from rest and now it's 14 meters per second. Very good. The opposite is also true. If I kick a ball up with a speed of 14 meters per second, as it rises, it slows down and eventually stops because all of the kinetic energy changes to gravitational energy. Can you find the height? Exact same working. So if I give you velocity and ask you to find height, or if I give you height and I ask you to find the final velocity, potential energy equals kinetic energy. That's the key to solving these types of questions. Next page. We're done talking about energy. Now let's talk about work. What is work? I hate that song, I swear to God. Every time I say the word, it pops up in my head. What is work? It's defined as the transfer of energy. I'm sure you know which song it is. And if it's not like in your mind right now, you are blessed, alhamdulillah, not cursed. Now, work is defined as the transfer of energy. You'll say, Mr. We already said you have like 4 different transfers, like earlier over here. So there's like mechanical work and like electric work and heating is considered work. Yeah, I'm talking about specifically work as an energy transferred by a force. So whenever I say the word work, assume that I mean by a force. So what is the work done by a force or so? We calculated using force times distance. Distance. That's very similar to moments, right? But the force and distance must be in the same direction. So if you're pushing a box to the right, the distance has to be horizontal. If an object is falling, like due to gravity or weight, the distance is actually the height. It has to be vertical. You're pushing a box up the slope, and I give you the force of friction on the slope. What is the work done against friction? It is the length of the slope. They have to be parallel to each other. Instead of saying same direction, I can say they have to be parallel to each other. Sometimes you'll see the term work done against a force. It's the same as work done by a force. Does not matter. It's still force times distance. The reason why we use the word against is because maybe the object is sliding down Like maybe in this case, you have a box that's sliding down a slope, but the force that's acting on it is friction, so it acts against you. And I want to know the work done against friction, meaning how much energy is friction trying to take away from you. It's also force times distance. Okay? So the word work done against or work done by shouldn't really confuse you at all. It's just work. Work, work, work. Now, defining what is power about. Sometimes my brain just like, define power. Or power. No. Power is defined as the work done per unit time or the energy transferred per unit time because work is energy. It's just how fast you transfer the energy. Oh, by the way, I forgot to mention, work is measured in what? Joules, because it's energy. So what is power? Power is work over time. I'm sorry. Power is work over time. It's how fast you transfer the energy. And it's measured in watts. This means that if you have a light bulb, and it's rated at 20 watts, this means it uses 20 joules of energy per second, every 1 second. It uses 20 joules of energy per second. That's what a watt means. That's what a watt means. So power is just work done over time or just energy over time. That's not hard. By the way, if I ask you, hey, you have two objects or like two motors and they're working, like they're doing work, they're lifting an elevator or something. If they're lifting the same mass up the same height, but let's say elevator A takes 10 seconds, whereas elevator B takes 30 seconds, which one has more power? As in, which elevator's motor is stronger, like has more power? A. Exactly. Because power and time are inversely proportional. The less time you take, the more power you have. The more time you take, the less power you have. Okay? Good. Final thing in this chapter is the concept of efficiency. Basically, efficiency, and if I ask you to define it, efficiency is just the ratio of the useful energy output divided by the total energy input, or power output or power input. Okay? So they're both fine. And it always gives you a percentage, but what does it mean? Take a look at this next diagram. Any energy transfer follows the law of conservation of energy. Energy cannot be created or destroyed, can only be changed from one form to another. But nobody said all of the energy transformed is useful. Sometimes the energy transformed is considered a waste. It's wasted. So take a look at this. Here's a light bulb. It takes in 60 watts of energy per second. So 60 watts of power. And it gives out 15 watts of light. Wait a second. Light is the function of a light bulb. So this is what we consider useful output. But light bulbs also emit some heat. So heat is considered what? Wasted. It's wasted. It's considered waste. So have I converted 100% of the power to something useful? It's not destroyed. It's just turned into something not useful with less heat. So no. Let's get the efficiency here. The efficiency here is 15, which is the useful, divided by 60, which is the total, times 100. This is a really crappy light bulb. 25% efficiency. 25% of the power was usefully transferred. The rest, well, wasted. Let's check out this light bulb. Maybe this is not a filament lamp. Maybe this is an LED, you know. Pick your favorite poison. Like, brand. Venus, for example, here in Egypt. LED. The advantage of LED light bulbs is that they don't heat up very much. So if you calculate the efficiency of this light bulb, it's the same light energy output, like it's the same 15. But the total energy input is 20, which means the wasted energy is only 5 watts, not 45 watts, it's only 5 watts wasted. Times 100, this gives me a 75% efficiency for this light bulb. It's much better. It's wasting a lot less. So if something is more efficient, it doesn't mean that it gives you more energy. It doesn't mean that it gives you more energy. It means what? My spelling is completely all over the place. It means that it wastes less energy. It means that it wastes less. Doesn't give you more. It just wastes less. So keep that in mind. Okay. Next. Moving on. Let's solve a couple of questions here, because energy, work, and power is actually a very important chapter. It's very common. You will almost always see some kind of energy question in the final exam. You have to. Figure 1.1 shows an electric-powered bicycle. When fully charged, the battery can deliver 600 watts for 60 minutes. Calculate the energy in joules. So we calculate the energy in joules stored when the battery is fully charged. I have power. I have time. I need energy. Oh, that's easy. Power is energy over time. So energy is power times time. Power is 600 and the time is 60. Wait, should I do something here? Remember what I said earlier? This entire chapter, you have to use SI units. Is minute an SI unit? You have to change the minutes to what? The seconds. I must change the minutes to the seconds, because all of these units, watt, joules, Newton, all of these are based on SI units, meaning mass has to be in kilograms, distance has to be in meters, and time has to be in seconds. All right? So 600 times 60 times 60. Now, I'll remind you, you can write your values down as they are, or you can change them to standard form. I prefer standard form to 3 significant figures because it allows me to avoid, miscounting zeros. State the form of energy stored by the battery. Inside a battery is what? Chemical energy. Easy enough. The bicycle has a motor with an electrical power input of 250 watts. Calculate the time for which the battery can power the bicycle. So now we have stored the energy in the battery. That's the charger. So the charger has a 600 watt charger. It's amazing. The motor, however, has a power of 250 watts. How long will the motor last? So again, power is energy over time. So time is energy over power. The same energy that we just got, so I thank God I didn't clear my calculator's memory, over power, which is 600. So divide that by 600. And wait, this gives me a more reasonable number. So I'm going to change it back from standard form to normal. That's 3,600. Since I'm using SI units, I don't need to think much. Seconds. Since I'm using SI units, joules, and I'm using watts, time is in seconds. Consider this bicycle compared to a small motorcycle. State 2 environmental benefits of the electrically powered bicycle. Oh, you're right. Absolutely. See, brain fart moments. You know, when you haven't eaten much, I'm hungry. I'm starving. What are you guys having for iftar? 250. Wait, I should act like all smug and say, haha, this was a test. And you guys passed it, shouldn't I? So 8,640 seconds. Okay? Yes, I should. Wait, I should have. Rewind. This was all a test. And you did not fall for it. Good job. Moving on. Consider the bicycle. Consider this bicycle compared to a small motorcycle. State two environmental benefits of an electrically powered bicycle. So this is kind of an interesting question about, environmental benefits of something. But what's the comparison between a motorcycle, which burns fuel, and the electric bicycle? Huh. What do you think are the benefits? First, the electric bicycle, because again, benefits immediately. The electric bicycle is what? Does not produce pollution. Exactly. So no pollution or less pollution, right? And then second, think about the fuel you're consuming. Hey, not a bad approach. Like you're saying renewable. I'm not going to use the word renewable though, because renewable is later on when we talk about power stations, okay? So because you still have to charge your battery. But you do not burn fuel. There is no fuel being used. So we don't end up using up the fuel that we have on Earth. So no fuel is being used. That's an environmental benefit. I don't have to consume more fuel. I don't have to dig for more oil, which then furthermore produces less pollution and less greenhouse gases. And by the way, instead of saying no pollution and less pollution, I prefer to specify the type. So less air pollution or no air pollution. Okay. Next, let's take a look at something else. Here's the next one. Water is held behind a dam in a hydroelectric power scheme. State the main form of energy stored behind the dam. We'll discuss this in a minute, okay? In a hot minute, but it's gravitational. So when you lift something up, when the water is lifted high up behind a dam, it's gravitational. You can use gravitational, or you can say the full term, gravitational potential energy. Okay? You don't have to say the word energy, because it's already mentioned, but still. The water is released from the dam and fall a vertical height of 410 meters at a rate of 480 kilograms per second. By the way, this is actually three values, not two. He's given me the height. He's given me the mass per second. He's given me the time, which is 1 second. Calculate the rate at which the energy is transferred by the falling water. What does rate mean? Rate of anything means that thing over time, which means he wants energy over time, which is power, by the way, if you haven't noticed. What type of energy, though? Well, it's gravitational. So what's the rule? mgh. It's mgh. Over time, which is 1 second. So moving on. The mass is 480. G is 9.8. Again, same thing. This was from 2022, so the value of G here is actually 10. And the height is 410 over 1 second, because the time is 1 second. So 480 times 9.8 times 410 over 1, which gives me a very long value, so I'll change it to standard form. 1.93 10 to the power of 6. What's the unit of rate of energy transfer? AKA power. What? What is the unit? Okay. Now, this next bit will show you two things. And one, energy questions can be combined with any other chapter, even things we haven't revised yet, like electricity. And two, we get to use efficiency. Okay. The power scheme, which is the entire power station, supplies a current of 270 amperes and a voltage of 600 volts. That's the output current and voltage. In Unit 4, in electricity, we will learn that electrical power is calculated using V times I, voltage times current. But I'm more concerned with What kind of power is this? Input or output? Go back to the design. This is a hydroelectric power station, which means it takes in the main form of energy, is gravitational potential energy, and it converts it to electrical energy. And it converts it to electrical energy. Okay? Good. So when I ask you for the efficiency, oops, my bad. When I ask you for the efficiency, it is the useful output, which is the electrical power, which is 270 times 6,000, V times I. This is from unit 4. Over the input, which is what we have, 1.93, 10 to the power of 6, times 100. So this is still a basic energy question, but the difficulty is in figuring out, it's like, oh yeah, that thing from electricity that we've studied, we can use it to get power, right? And the fact that this is power output. You will end up with 83.997, so 84 is a good answer. 84% efficiency. That's not bad, right? That's quite decent for a power station. Okay. Moving on. Very easy chapter. Literally in your face. What is pressure? When you stab something. Oh, actually, that hurt. When you stab something, like if I stab my hand with a pen, because of this very small surface area of the pen, the force that I apply actually hurts and could actually cut through my hand, right? When you have a nail and you hammer it into a wall, the reason the nail can get hammered through a wall is because it has a very small surface area. But if I try to push the end of my pen onto my hand, which is flat, by the way, it does nothing. It doesn't hurt at all. If I try this with a sheet of paper, like I have an old sheet of paper here, if I try to stab this piece of paper with the back of my pen, nothing happens. But if I try to stab it with the tip of my pen, it immediately what? Goes through. We poked a hole through the paper. It doesn't show up much, but we poked a hole through the paper. The effect of focusing a force over a specific area, large or small, is called pressure. So pressure is force over area, force per unit area, F over A. The unit of measurement of pressure is called Pascal, only if you use SI, meaning Newton per meter squared. Newton per meter squared. Basically, what we've just described is the fact that the area and the pressure are inversely proportional. The smaller the area of this pen, for example, the greater the pressure it applies, which means it can cut through things. And the larger the surface area of the force, or the force is spread over, the less pressure you get. So it doesn't cut through anything. Okay. This is the general equation for pressure. What if the pressure that we're discussing is the pressure of a liquid or caused by a liquid? When I dive underwater, the water above my head has weight, and the weight of that liquid, boom, applies pressure on my head. But the pressure of a liquid is not calculated mostly by force over area. We can, by the way, if we measure the force in area, but it's actually calculated using rho GH, where rho is the density of the liquid, which means it's affected by density. G is 9.8, and H is the depth of the liquid. I know it's called H, height, but it's actually depth. Depth meaning we measure the distance from the surface going down, not from the bottom going up. That's not what we measure. We measure it from the top of the surface going down to where you are. That's the height or depth that we measure. Okay. So according to this rule, the pressure is affected by the depth. If the depth increases, the pressure increases, and it's also affected by density, right? If the density increases, sorry, here you go. If the density increases, the pressure also increases. Finally, though, if I ever ask you about the total pressure, not the pressure, the total pressure under a liquid, you need to understand that there are two pressures acting on you when you're underwater. The pressure of the liquid normally, which is rho GH, that's fine. And then the atmosphere itself, the air, also applies pressure on the surface of the liquid because the air molecules are colliding with the surface and they're supplying pressure. So if I ask you, what's the pressure of the liquid? Rho GH. But what is the total pressure? The total pressure is rho GH, which is the liquid, plus whatever the given value for atmospheric pressure is, which is usually 1 times 10 to the power of 5, 100,000. Usually, but it's not always the case. The questions can change that value because it changes based on temperature and so on. So, and altitude. So keep that in mind. Quick question about here. Here's a hydroelectric power station, which we will discuss again shortly. And the first bit is the same question we use. What is the form of energy stored in the water of a reservoir used to generate electricity? Like the energy stored behind the hydroelectric dam is gravitational. It's fine if we combine chapters, by the way. But now, keep what we mentioned earlier in mind. The turbine is 150 meters below the level of the water. That's the height or depth. The atmospheric pressure is 1 times 10 power 5. The density of the water is 1000. Calculate the total pressure in the water. Not the pressure of the water, the total pressure in the water. So how do we get pressure of a liquid? Pressure of a liquid is rho GH. Density, which is 1000, times 9.8, times, what was the height? 150. So this gives me a pressure. Is that my answer though? No. Why? This is a big number, so this is 1.47, 10 to the power of 6. That is not the final answer because the total pressure is the liquid pressure plus the atmosphere. Liquid pressure is the answer we just got. Atmospheric pressure is 1 times 10 to the power of 5. So I'll add 1 times 10 to the power of 5, which gives me 1.57 times 10 to the power of 6 Pascal. So the total is the sum of the liquid pressure and the atmospheric pressure. The turbine has a cross-sectional area of 3.5 meters squared. What is the force exerted on the turbine by the water? So you might say, but this is in a liquid. Yeah, I don't care. Pressure is always force over area. So if I ask you for force and I give you the area, just use the rule. Pressure is force over area. So F is equal to what? Pressure times area. Just rearrange the formula. The pressure down here is 1.5 what? 7? Okay. 6 times 3.5. Oh, I already have that, so times 3.5. 5.5 times 10 to the power of 6 newtons. If you don't like standard form, write down the value normally if you want to, but just make sure you do not forget any zeros. The water flows to the turbine through a pipe of constant cross-sectional area. Explain why the kinetic energy of the pipe remains constant as it flows through the pipe. Because what? Why would the speed stay the same? Kinetic energy means the speed. Kinetic energy means the speed. So why would the speed remain the same? I want you guys to guess just a little bit. No one? Really? Because the A. What is constant? You're on the right track. Because what is constant? Hmm. Distance is constant, cross-section area, pressure is the same. You're heading in the right tracks. But honestly, this is a trick question. It's not really an energy question at all. It has less to do with energy, less to do with energy, and more to do with, you know, the state of matter. Here's the thing. The water has a constant cross-sectional area. That's my key. Thank you. Good job. The density is constant. So if the area is constant and the density is constant and the mass that flows through is going to be constant anyway. So the speed is going to be constant. But I have a question. If the pipe was a bit thinner, like if instead of having a uniform thickness, the pipe was a bit thinner and the mass has to be the same, like the density has to be the same, so the mass has to be the same. So what's going to happen to the speed of the water that goes through the thinner pipe? Has to speed up, right? So this honestly is more of a trick question. It's there to cost you a few marks. So explain why the kinetic energy remains constant. You can at least get 1 mark because the speed of the water is constant. Like that's one thing. It's like kinetic energy is constant, the speed is constant. But why is the speed constant? Because the density and mass of the liquid flowing through is constant. Like the amount of mass that passes through per second or per unit time is constant, which means the water doesn't get compressed, it doesn't get it can't get compressed anyway. So if the area is constant and the density is constant and therefore the amount of mass that goes through is constant, so the speed has to stay constant. Very good. This one's more about descriptions. How do I know that they're constant? Because can you compress a liquid? Are liquids compressible? By the way, that could be your answer. If you don't want to say, oh, density and mass of liquids is constant, you can say liquids cannot be compressed, right? You can't compress a liquid. So if the area of the pipe is constant and liquids cannot be compressed, this means that the mass of the water going in has to be equal to the mass of the water going out. You can't really compress it to make more mass or less mass go in or out. So the speed stays the same. So, good. Very nice. Good question. Figure 3.1 shows a person moving across an ice-covered pond to reach a ball on the ice. I don't want the ball. Explain why this way of moving across the ice is safer than walking. Use your understanding of pressure, meaning write down the equation of pressure. So we'll say, since pressure is force over area, this way of moving increases the area, which decreases the pressure, so the ice doesn't break. You have to mention the rule. Him asking you for your understanding of pressure is what's the rule? And then explain the basic concepts, the two things. So it's like, oh, area is larger, so pressure has decreased. And then finally, this one was a doozy. I remember getting this in a test once, and people were just like, oh, they just went crazy, thinking of this is way too hard. It's not very hard, by the way, but you need to understand the whole total pressure concept a little bit differently. Figure 3.2 shows a side view of a pond with a layer of ice floating freely on the water. The surface area of the pond is, you have the area, is 5. The mass of the ice is 690. With the mass of the ice, I can get the weight of the ice, which is 690 times 9.8. The density of the water is 1,000. Point X is 0.45 meters below the ice. That's the height. Calculate the pressure at point X. Look at the language. Look at the language. Due to the ice and the water. So there are two pressures that I'm calculating here, and then I'm adding them up. The pressure of the ice and the pressure of the water. And then I add them. Pressure of the ice, that's a solid. Force over area. Do I have the force? Yes, I do. The weight of the ice. 690 times 9.8. Do I have the area? Yes, I do. It's 5. Done. Over 5. Which gives me, change it back from standard form, a value. Good. Then the water. Good job. Water is a liquid, so rho GH. Look at this. One question has both equations. 4-mark questions aren't hard per se. You just have to do a lot of work, do this basic working a lot. Getting the weight is worth a mark. Getting force over area is worth a mark. Rho GH is worth the next mark, like getting the pressure of the liquid is worth the next mark. So 1,000 times 9.8 times a height of 0.45, which gives me 4,410. And then I add them. Plus 1352.4. This gives me 5,762.4 Pascal. Or just 5,760 is fine. 3 significant figures is fantastic. We'll talk about mark schemes and why do they round up or round down and stuff later. Okay. Good. Next, final thing that we want to discuss. Power stations or energy resources. All right. All the energy resources we will discuss are mostly used to generate electricity. And almost all methods of generating electricity, except for solar, use a combination of devices called a turbine, which is like a big fan. If any kind of fluid hits it, so wind, water, whatever hits it, it turns. And the turbine is connected to a device called a generator. From unit 4, a generator has a coil inside, and when the coil spins in a magnetic field, it generates electricity. The entire concept is us getting a flowing liquid or gas somehow to hit that turbine, making it spin, and the generator spins, and it generates electricity. Okay? So let's start with my non-renewable power stations, because it's split into 2 types, renewable and non-renewable. So first here, the first is my chemical power station. When I say chemical, I mean I use fossil fuels. So we burn the fuel burned boils water inside a boiler. The water turns to steam. The steam then hits a turbine, like moves through very thin pipes, hits a turbine. Turbine spins, the generator spins, it generates electricity. The water then condenses and goes back to the boiler, and we have a cycle. The important thing is, what is the energy transformation here? Chemical in the fuel, to heat, because we burn it, to kinetic, because the steam moves and turns the turbine, to electric, because the generator gives out electrical energy. So it's reliable, meaning you can generate electricity 24/7, that's the advantage, and it produces a very large amount of energy. By the way, this will be the advantage of both non-renewable power stations. The disadvantage is that it causes air pollution, causes greenhouse gases, it's a non-renewable source of energy, which means eventually we will run out of fuel. Okay, next. Now, instead of burning fossil fuels, we can also use nuclear fuel, specifically uranium. What we do is we put uranium inside something called a nuclear reactor. Nuclear reactor undergoes a reaction called nuclear fission, or fission sometimes. So nuclear fission is when you break a nucleus of uranium. We usually do that by like firing a very small neutron inside, and it like breaks the nucleus and it creates a chain reaction that breaks all the other uranium atoms or nuclei. But that reaction converts nuclear energy to heat. The rest is the same story. The heat heats the water boils, turns to steam, the steam hits the turbine spins, spins to the generator, generates electricity, water condenses, goes back. Same story. With the same advantages. It's reliable, meaning it works 24/7 regardless of the weather, and very high energy output. The disadvantages is that you could die. This power station could explode if mishandled, or the waste that remains is radioactive. It's ionizing, which can cause cancer. And uranium is a metal that's non-renewable. You dig it from the ground. Everything else is renewable. So let's start with one that is very similar to coal and like fossil fuels and nuclear, geothermal. I should have probably highlighted these. Geothermal. We use the heat from rocks under the ground. That is your source of heat. Underground, if you dig deep enough, the rocks underground eventually get hot enough to boil water. So you dump the water underground, the water fills the space up, boils, turns to steam, steam rises, the steam spins the turbine turns the generator produces electricity. So there's no source of energy like a fuel that's consumed. It's immediately heat to kinetic, because the turbine turns, to electric. It's renewable and reliable, and it doesn't produce any kind of pollution, which is fantastic. You'll say that's the best. Well, here's the thing though. It's extremely hard to find a place where the rocks are hot enough. You can't find it anywhere. You actually have to go to places which were, let's just say, volcanically active before. Because you can dig a little bit there. Iceland has, yes, because it used to be very volcanically active. Sure, if it still is, but still, very thin crust. You dig a little bit deeper and you find some hot rocks. Waves. What's a wave turbine? We literally put floating turbines. Floating turbines in the water where there are strong waves. So when the waves hit the turbine, they spin or they vibrate up and down. Sometimes they're called buoys as well. They vibrate up and down, which turns a generator. The generator is either on the seabed or inside. It doesn't matter. So as the turbines turn, the generators turn and they generate electricity, meaning it's just kinetic to electric. There are no other sources. You take the kinetic energy from the water, turn it into electrical energy. The advantages here is that it's also renewable, no pollution, which is probably going to be the advantage of almost every renewable power station, pretty much. The biggest disadvantage of almost all renewable power stations, except for geothermal, is that they are unreliable. Why? It depends on something. In this case, depends on the waves and their speed, because that depends on the weather. I can't guarantee the weather. And it also produces low energy output. It's not very good. I need a lot of it to produce enough energy. All right? So using water as well, let's talk about tides and hydroelectric stations, because they both are basically the same. A tidal power station uses high tide and low tide, like the difference in water level in the ocean, to generate electricity. We build a dam in the ocean, so we have a big empty space called a reservoir. When there is high tide, the water level outside of my dam is very high, which means the water has gravitational potential energy. My reservoir is empty, so the water starts flowing in. And what do you know? We put a turbine in the way, which turns a generator and generates electricity. So it's gravitational, because the water has gravitation as it flows down, it turns to kinetic, to electric. Same thing, renewable, doesn't cause pollution. Disadvantages, it's unreliable, because it depends on the tide. That's not fixed. It depends on the tide. And it produces a low amount of energy. And it's also difficult to find the location to properly build. It's hard to build. What is hydroelectric? Hydro means water. Electric means electric, electrical energy. So electricity from water. We have this in Egypt, the high dam, remember? Last one. We build a dam which stops the flow of water. This causes the water level to rise. It's in a lot of places too, by the way. When the water level rises, this means you have now stored gravitational potential energy. When we allow the water to flow down, this turns to kinetic energy, which turns the turbine, which turns the generator, generates electricity. The advantage is that it's renewable, it doesn't cause any pollution. It's unreliable as it relies on, the flow of water and the rain cycle. Without rain, you don't get lakes or rivers. And it's hard to build. The last two are very simple. Solar panels or solar cells, not solar heaters, okay? Solar cells just convert light to electricity. Done. That's all they do. There are no moving parts. There's no turbine and generator. This is the only station with no turbine and no generator. The solar cells chemically react with the sunlight and produce electricity, like immediately a current or a voltage. It's also unreliable. So it's renewable, no pollution. It's also unreliable because it relies on day and night cycle. It doesn't generate electricity at night. Or if it's, foggy or if it's cloudy, no more sun. And it needs a lot of space to produce enough electricity. Finally, we use wind turbines. The wind, which is from the atmosphere, like the motion of the atmosphere, hits these turbines. And what do the turbines do? They spin, which spins the generator connected to them, converting kinetic to electric immediately. Again, no more steps. It's renewable, it doesn't cause pollution, but it's unreliable because it relies on the wind speed, and that depends on the atmosphere. Needs a lot of space, low energy output, the same disadvantages. Good. Now, one very common question that you'll often be asked is, which sources of energy come from the sun? Everything comes from the sun, except for geothermal, because that comes from the core of the earth. Nuclear, which is again from the earth itself, from the ground itself. We dig up uranium from the earth. And tidal. Tidal energy, or like the high tide and low tide, depends on the moon. So both of these come from the core of the earth, like the body of the earth itself, and this is from the moon. The gravitational field of the moon is what causes high tide and low tide. However, everything else, the sun is the source of energy of. Like fossil fuels. This is a stretch, even for me, but fossil fuels were living creatures like plants and trees and like animals that died. But the reason they were alive and they had energy was because of the sun. So when they died and they decomposed and became coal and oil and gas, the energy there is from the sun because they used to eat plants. Like animals would eat plants. So plants get energy from the sun. So everything depends on the sun. Hydroelectric, how does that depend on the sun? The sun is what causes the rain cycle, evaporating the water in the ocean, creating clouds and rain, which forms lakes. So all of this comes from the sun. Wind comes from the sun because wind is the flow of the air in the atmosphere due to temperature and pressure differences in the atmosphere. So when the sun heats up one part of the atmosphere but not the other, this causes the atmosphere's pressure to change. One side is higher pressure, one side is lower pressure. So it starts moving from high to low pressure. Solar, I mean light from the sun. So that doesn't need explanation. It's from the sun. Let's finish this up by solving a question or two. Figure 3.1 shows the cross-section of a barrage built across a tidal bay. The barrage is part of a tidal power station. The gates are raised to open whenever the tide comes in. The gates are lowered to close when it's high tide. Figure 3.1 shows the water levels in the open sea and the tide bay when it's low tide. The gates are raised and the water flows through the turbine. Complete the sentences to describe the energy transfers that take place. Use words from this list. Dash energy of the dash. Good job. In the dash is transferred to dash energy in the rotating dash. Let's start from the very back. What's rotating? What's gonna be rotating? The turbines, right? So turbines rotate. What kind of energy is in the turbines? Dash energy in the turbines. Kinetic, right? Then dash energy of the dash in the dash is transferred to what's all this? What kind of energy does the water have because it's high up? Because that's the first type of energy. Gravitational potential. Of the what? If we go back to the diagram of the water in the where? Tidal bay, not in the open sea, in the tidal bay. So that's why it looks a bit confusing because that empty spot is something in the diagram. So gravitational potential energy of the water in the tidal bay, right, is transferred to kinetic energy in the turbines, which is then used to generate electricity. State one advantage and one disadvantage of tidal power as a resource. Ooh, advantage. Renewable. Disadvantage. Unreliable. Or does not generate electricity 24/7. State the main source of energy for tidal. The sun. Right? Huh? Right? Huh? This one's on purpose. Is tidal from the sun? No, bravo. Tidal is from the what? The moon. Good job. Good job. See? Everything's calculated. State two energy resources for which the sun is not the main source. So three things. We just mentioned tidal earlier. So tidal is not from the sun. Geothermal isn't from the sun. And just for the heck of it, nuclear as well. Only write two. I'm writing all three so that we revise, okay? State and explain whether each of the following methods of electrical power generation is renewable. So consider if it's renewable or not and explain why. Anything renewable, most things that are renewable have to eventually come from the sun, except for, tidal, which comes from the moon. And geothermal comes from the earth. You have to describe that. Power generation in a nuclear power station. Oh, nuclear is non-renewable. Why? Because it uses uranium, which is obtained from the earth, and it can run out. So the fuel that we use, if you forget uranium, you can just say the nuclear fuel that is used comes from the earth and it can run out. Power generation from waves in the sea. This is renewable. Why? Because the wind is what produces the waves, by the way. Because what produces waves? The wind. And what produces the wind? The change in temperature of the atmosphere due to the sun. So the wind that produces waves is due to the sun, which is a renewable source of energy. So I have to mention how the waves come from the wind. And the wind is renewable because it comes from the sun, so it's renewable. And that, ladies and gentlemen, is the end of Unit 1. Finally. See you for Unit 2.